Hi there. In this video, we're going to use some of the properties that we saw in the last video about even and odd functions to help us evaluate a couple integrals of trig functions that are going to be really useful to us as we go and talk about Fourier series. So the problem that we have for this video is we want to evaluate three types of integrals. So evaluate the following when m and n are non-negative integers. So three problems. One, we're going to go the integral from negative L to L. And we remember seeing L as the length of our wire in the heat equation and the wave equation in the last section. So we're going from negative L to L of sine m pi x over L cosine n pi x over L. 2 is going to be the same thing, except both of them are going to be sines. Sine m pi x over L and cosine n pi, that should be sine n pi x over L dx. And our last one is the same thing, but both cosine. So cosine m pi x over L and keep doing it. Cosine n pi x over L dx. Now the m pi x over L and the n pi x over L are a little bit scary, I guess. But this is just sort of a squishing of the sine and cosine functions. So this has period. All of these have period. The regular period of cosine x or of sine x divided by the stuff that's in front of the x, the thing that's multiplying by x here. So over n pi over L, which is just equal to the pi's are going to cancel, and you are left with 2L divided by n. So you just get the sine or cosine squished into the negative L to L a bunch of times. And we have an example of this. Here we go. This figure is in the book, in the section. And you can see that for both your cosines and sines, you have, depending on what your m or n is, 0, 1, 2, 3, you just get your regular cosine and sine, but squished into a negative L to L, whereas you're used to seeing it from negative pi to pi. But it's going to be a lot easier because you don't always have wires of length pi. It's a little bit easier to think about it in generalities here. So the bigger m and n are, the faster you're oscillating here. Now, okay, so we want to calculate all of these integrals. And if you really want to do the integration, then you can go watch the Khan Academy. Here it is. I'm pretty amazed that we can bring up a browser window in this app. But they've got all of these different integrals on Fourier series. So you can go and get the introduction to this if you like. And then this is exactly the first thing that they do. They look at these integrals of sine of mt and cosine of mt, and then the integrals of sine times and sine times cosine and sine times sine and cosine times cosine, exactly the thing that we're doing. And they sort of go through this in excruciating detail. So here you go. He's actually going to do this integration and do the antiderivative and plug in the limits and all this stuff. So if you want to see that approach, you can go and watch these videos, and I do recommend that you do that. And even watching the whole series on the Fourier coefficients and Fourier series, it's another perspective. But we're going to think about it in a little bit more intuitive sense. Okay, so let's go back to our integrals. And we have that our integrands are products of sines and cosines. And that's going to be a lot easier if we can think about it as sums. So we're going to use, I've just pasted these trig identities from the book. And so this is going to break all of our products into sines and cosines of, m minus n pi x over L, blah, blah, blah. And so we get all of these terms that look like this. And if m and n are integers, then so are m minus n and m plus n. And so this is just some integer multiple of pi x over L. And so all of these things in the red box, each of these are basically pictured in this figure down here. So if we're integrating the stuff on the left-hand side, then that's the same as integrating the stuff on the right-hand side. And so we can pull out the 1/2 from the integral. And so now we're sort of concerned about what is the integral of one of the things in the red box from negative L to L. So let's think about what if we integrated all of these plots from negative L to L dx. What would we get? Well, mostly we'd get 0, because these are all periodic functions that are doing the same thing above the x-axis as they are below. So if we've got all of this stuff happening in the top, blah, 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 we're getting the exact same stuff happening in the bottom over the course of a single period. Let's see, yeah. And so this is going to integrate to 0. This is going to integrate to 0. All of these that actually do are oscillating. Sine of 0, now the 0 case is a little bit different, so sine of 0 is just 0 anyway, so that one is going to die off when we integrate it. And so the only one that we are going to get something a little bit different here is cosine of 0, which is just the function 1. And so if we integrate that, we're going to get 1 times the length of the interval, which is going to be 2L. Okay, so let's summarize. All right, we'll move that out of the way. And so for integral 1, we get the integral from negative L to L sine mx, m pi x over L cosine n pi x over L dx. And I can write that out using my trig identity. So I've got 1/2 the integral from negative L to L of sine m minus n pi x over L dx plus 1/2 integral negative L to L sine m plus n pi x over L dx. But remember, all of the sine integrals from our figure down there were 0 when we integrated from negative L to L. And so this is just going to equal, let's make this a little smaller, equal 0. Okay, so those, when you get a sine and cosine, those are all going to die. Okay, so number 2, integral negative L to L sine m pi x over L sine n pi x over L dx. So now we use our trig identity and we get 1/2 integral negative L to L cosine m minus n pi x over L minus of dx minus 1/2 integral negative L to L cosine m plus n pi x over L dx. All right, let's clean up here for a second. Okay, so this one is going to depend a little bit on what m and n are. So if m and n are both 0, so if m equals n equals 0, then both of these integrals are going to be the same thing. And so this thing is going to cancel out to 0. And you could see that if you plugged it into the one on the very left-hand side there, because you would just get sine of 0 times sine of 0. And so that the whole integrand is going to be 0. Okay. And then if m equals n, but they don't equal 0, then this one here is going to equal 0, because you'll get cosine of m plus n, which is sort of not one of our zeros. Remember, we're only going to get something non-zero as an integral if what's inside the integral is cosine of 0. And this one is because m plus n is not equal to 0. But what you do have here, m minus n does equal 0. So this integral equals 2L, and we're dividing it by 2, so this whole thing equals L. And so in this case, that m equals n, but this does not equal, but they both are not 0, then we get L. And then the last case, let's delete this stuff here so we can do our scratch work again. So our last case is going to be if m does not equal n. Oops, I lost my L here. So now, if m doesn't equal n, then by the same reasoning before, this is just cosine of something non-zero. Let's just say this equals 0, and then this equals 0. And so the whole thing is going to equal 0. So that's the answer to that particular integral. And yeah, I'm going to lose it. So we got L and 0 if m does not equal n. Okay. And then our last one is going to be really similar. There we go. So we've got negative L to L. Now we've got cosine m pi x over L, cosine n pi x over L. And this equals the 1/2 integral of cosine m minus n pi x over L dx plus 1/2 the integral of cosine m plus n pi x over L dx. And we'll just do things down here. So again, we're going to have the same cases if m equals n equals 0, if m equals n not equal to 0, and if m does not equal n. So in the first case, where you get 0, both of these are going to equal L because they're both cosines and we don't have a minus anymore. So we get a 2L in that case. Then in the case where m equals n, but they are not equal to 0, then m plus n is just going to be something non-zero, and so this is going to equal, that's going to go away. And this guy, including the 1/2, m minus n will be 0, so then we'll get a cosine of 0, and this thing will equal L. So we get L right there. And then in our last case where m does not equal n, we still get this equals 0, and m minus n now is non-zero, so this is also going to equal 0. And so we get a 0 down there. And that is the answer. So it may seem like a little bit silly why we did this long trig exercise, but these calculations are going to come in really handy when we actually get into Fourier series in our next video.